All right, so yeah, welcome everyone. Thanks for joining us today. I'm Robert Green. I'm with Product Management at Oracle, working with the NoSQL Database team. So today I'm going to give you a technical overview on the NoSQL Database. We're going to first start with a little background on NoSQL, just for those who may not be familiar with it. And we'll take a look at NoSQL within Oracle and what's going on with the technology and how it's integrating with the rest of the Oracle technology stack. And then we're going to dive down into the details of developing with the Oracle NoSQL Database. Take a look at its architecture so you can understand how it operates. Take a look at deploying a cluster with the technology, and then take a look at developing an application and some of the issues that you'll encounter in that process. And if we have time, we'll take a quick look at use cases. So the Oracle NoSQL Database is a NoSQL database, which is inherently a scale-out type of database, which is meant to run across lots of independent pieces of hardware, and instead of scaling up on one massive piece of hardware. And in addition to that, it's a key value database. It supports ACID transactions that you would expect from a database from Oracle, but at the same time, it also embraces what's known as BASE, which is basically available consistency model that's found in many of the NoSQL products, which can give you a little bit more performance in certain conditions where you can afford to relax your transactions. So anyway, in addition to that, it's highly available, it's always on, it's elastic, it's pretty simple to administer, especially given that it's such a complex technology. And so anyway, we're going to go into the details of it in this presentation. So first, again, a little background on NoSQL. So for those of you who aren't familiar with NoSQL, we'll just briefly talk about where did this stuff come from and what is it. I mean, if you look back at traditional business, 15, 20 years ago, traditional business really was kind of an internal facing operation. It was often involved with accounting practices, managing contacts with customers that you're selling to, looking at your inventory and managing your employees. So it was a very fixed set of data, basic data, and all that data was targeted at operating the business, and it was largely input by people. I mean, it was people sitting at keyboards with very specific applications, interacting with the software and generating the data that was part of that traditional business. And so as technology evolved, it started moving things forward in such a way that new data was beginning to get created, and the businesses were starting to react faster because it had more information coming to it quicker. And so you see this emergence of modern data, which is social in nature, or public repositories of data, like the National Weather Service, starting to populate weather data inside big repositories, and then giving public access to that data, and other machine generated data from sensors and satellites and things like that. So all this new data started getting generated, and it was coming in very, very quickly, because it's not just being generated by people interacting with basic business systems, but it's coming from consumers and from large stockpiles of data, etc. And so as all this new data started coming in, businesses started wondering, how is it that they could become more competitive based upon all this new data that was becoming available to them. And so they started thinking about how is it that they could be smarter businesses, more agile businesses, and compete more effectively by leveraging all this new data. And so there came the emergence of what's been popularized as the big data trend, and leveraging that big data, which is your data of volume, of velocity, and variety. Businesses creating better program management, turning to just-in-time manufacturing, looking at social marketing in order to improve their outreach to the customer base. So looking at a whole new set of approaches to business, which gets them to leverage that data that's coming in. And so that's really what birthed NoSQL. It was this whole movement from very, very basic, human-entered kind of data into very, very modern and social and machine-generated data, and then businesses trying to stay competitive and make use of that data. So it brought in all these new data requirements, and with that, it brought in a new requirement for data management. And so, many companies, in an effort to stay competitive with this big shift, have started embracing this technology and bringing it into the infrastructure underneath their product offerings in order to bring that smart, agile business to their customers. So what's changing? I mean, how is it that NoSQL and big data is impacting our business today? So the traditional business and traditional relational databases, that SQL type of access, very well-defined schemas with high security access to the data and backups and analytics and all those things that we depend upon to run the business. But as things get more competitive, companies are needing more flexible schema management because the kind of data that's flowing at them is fairly unstructured or semi-structured in nature. Increasingly, these businesses are operating in a globally distributed manner, so they want to be always on and available to their consumers. And then a lot of data is flowing in very, very fast, and the faster that they can ingest that data and then pull it back out and understand it, the quicker they can react from a business perspective and take competitive advantage. And then finally, there's just a ton of this stuff flowing in, so it's a lot of data, and since it's not well defined in terms of its schema, it's really hard to try to stick all that stuff inside a traditional relational database. So you'd rather be able to just put all that stuff into lots of commodity machines rather than one great big expensive box in order to keep your total cost of ownership down. And that's really what's driving NoSQL database technology. It's NoSQL database technology is giving you this ability to have more flexible schemas and to use sharded and replicated database architectures to get global distribution and to deal with this fast data and ultimately deliver you a lower total cost of ownership. And in addition to NoSQL databases, there's also, I'm sure you're aware of, Hadoop, which is it's clearly big data. Some people consider it in the NoSQL space as well. But it's helping you deal with distributed processing of very, very raw data in basically storing it into file systems and doing very, very parallelized processing on it. But Hadoop is on the batch-based side of things, whereas the NoSQL database technology is really much more real-time. So where is this stuff used? I mean, the traditional business again and traditional relational database technologies. And so you've got traditional applications. I mean, you've got your ERP systems and your CRM. We talked about inventory control and accounting. So, all that stuff that you're familiar with. And as we look at all these new requirements that are flowing in because the new data is coming at us and the business is trying to stay competitive and take advantage of that, you get to the NoSQL database technologies. And the kind of applications that are using that technology are ones that are distributed in nature, dealing with web scale type of applications that you see, guys like Amazon and dealing with very, very large consumer bases, and real-time event processing where you've got very, very high speed data flow coming at you and you're trying to look up a history of events that are going on and do some correlation, or just dealing with mobile data or sensor data capture. There's a number of different places, but it's not the traditional type of application where you've seen a traditional database used in the past. So within Oracle, let's take a look at NoSQL within Oracle. I mean, first of all, the NoSQL landscape is getting increasingly large. You've got a ton of companies that are out there who are leveraging this technology. And it started with a few pioneers who kind of built their own. So when you looked at Amazon and LinkedIn and Google and these guys, they actually built their own sort of NoSQL technologies internally in order to help them deal with some of these problems that we talked about in terms of schema flexibility and always on and all of that stuff. But after those guys popularized their use of that technology, a whole bunch of companies have now started to adopt NoSQL technology into the enterprise and helping them stay more competitive in the modern landscape. And so from an Oracle perspective, we continue to invest in NoSQL. It's a key data management technology for us, and so we're constantly improving the technology and integrating it with our stack of products. So one of the advantages you get by looking at NoSQL with Oracle is the fact that we are very in tune with the requirements of the enterprise. And so we're not just delivering the technology in isolation, but we're delivering it as an integrated piece of software with the other pieces of software that you're going to need to build solutions. And so, we have these integrations into technology like Hadoop because these things often play together, but we're also integrating it with technologies like Oracle Spatial and Graph. We're integrating it with the Fusion middleware stack for our Oracle Event Processing technology, where you've got high-speed events that need to get captured and analyzed. And then we're integrating it with our caching solutions and creating all the connectors that are necessary to bring all of this data together and sometimes moving it right back into traditional relational database systems as well, because there you can do your SQL type of access to the data, and you can do some of your normal analytics and reporting and all that stuff. So the need is to get all of this data integrated in a way that you can deliver a complete solution, and that's what the enterprise needs. It needs something which integrates all this technology together and gives you a cohesive way to manage all that infrastructure. And that's what Oracle's bringing to the table with its NoSQL stack. So now we'll look at developing with the Oracle NoSQL Database. And as we talked about before, we'll look at the architecture and sort of a quick high-level overview of features, and then we'll get down into some of the dirty details. And so this is a picture of the logical architecture of the Oracle NoSQL Database. And what you see here is, it's an application with a driver. It's a library that you link into your application. And that driver gets you connected to this store. And inside the store is basically a bunch of data partitions. And those partitions are isolated. They don't share anything. All of the data is separate from each of those. And so basically data is hashed into these different partitions, and then each one of these partitions is independently responsible for replicating the data some number of times for reliability purposes. And so these partitions are actually elastic in nature, so you can add more of them, or you can split them, or you can contract them, and to the application space, it can't tell. It just grows and splits and rebalances itself as necessary. Writes are directed at a particular node which is elected at the time to handle all the write operations within one of these given partitions. And then from that elected node where the write is taken, it replicates out to all of the other nodes which are handling the availability. And then at the same time, read operations can actually read from any one of these nodes in the entire store. So you can see that to scale this, just from a logical architecture perspective, you would add more partitions. You would split your data out into a wider partition set. That gives you more nodes to write to, so it gives you a higher throughput in write operations. And at the same time, you have more replicas underneath all of those write partitions, which gives you a very large number of nodes to read from in order to improve your overall read throughput and reduce your latencies. So when we take a look at the physical architecture, it looks quite different than the logical one. And that's because basically we're taking the processes that are underlying this store and we're deploying them onto physically isolated units of hardware. And so in this case, we're showing zones 1, 2, and 3, which are racks in this theoretical data center. And so those partitions of data from the logical perspective are actually spread across these isolation units. So you can see the dark gray, the light gray, and the almost white represent your different partitions, but they're actually spread into different isolated hardware zones. Okay, and that protects against failures. So you get a couple things in this architecture. First, that driver, which is linked with your application, it's actually monitoring all of the processes in the store, keeping statistics about how much work that they've got in their queues, and about how long they're taking to respond to requests. So as operations are going on in the application, it intelligently directs those at the processes which are going to give you the best response. Plus, one particular node in one of these isolation units will act as a master for your write operations, and then replicate everything else out to the other nodes in different hardware zones. And by doing that, you get this always on highly available system, because any one of those nodes can fail, and because of a hardware or a disk problem, or a switch goes out, or whatever it might be, and the other nodes will take over from an availability perspective. So obviously you can deploy those isolation units in different ways, and in the first image we showed you, you're laying your isolation units out on racks in a given data center, and that gives you a certain amount of protection from a local perspective. But you can also lay those out in geographically disparate regions where you get the same kind of behavior, except you can actually take an entire data center outage and still survive and still be always on. So one of the things that this architecture also gives you is this elasticity. So you just give it hardware resources, and those hardware resources will automatically get incorporated into the running application space and instantiate these new partitions, and in that process increase your write throughput and decrease your read latencies. So it's just automatically expands simply by declaring new hardware resources. So another important feature of the Oracle NoSQL Database is this automatic failover capability. And this is where all the partitions that get instantiated in the store have a replication associated with them. Typically it's an odd number of copies in such a way that if one of them fails for some reason, due to hardware or software or power or whatever it might be, as long as a majority of the nodes remain operating, then the overall system will continue to service read and write requests. And then one of the more distinguishing features is the ability for us to have very, very flexible transaction control in the Oracle NoSQL Database. Basically, you can control things on an operation by operation basis. And the way that that's done is that you can configure your writes to either go into just the memory space of your database server process, or you can have it flushed all the way through your server process into your file system buffers, or you can have it actually synced to disk. And at the same time that you're doing that with the master, you're making that choice with that node that's taking the write operations. You can also, for the rest of the store, say how it is that you want to get acknowledgement from the rest of the replicas. You can either say, I don't care at all about the replicas. As long as I've written it to disk in the master, then I don't need any acknowledgement. Or you could say, I'd like to at least have the majority of those replicas say that they've gotten that operation as well. And then finally, if you really want it, you can say, no, I want everyone to acknowledge that I got it. So I want it written into the disk of the master. I want it written into the disk of all of these replicas as well, and I want it to respond to me before I let that operation return to the application space. And and obviously, on the left, it's the fastest, because you're just writing into memory and you're not acknowledging from anyone. And on the right, it's more like a traditional database system, but you have that flexibility to pick it on an operation by operation basis. Okay, and then when it comes to the reads, you also can get the same kind of guarantees of read consistency. I mean, you can say, hey, I'll take it from anyone. I don't care how out of date it might be. I just want to read. Or you can say, I want to make sure that the whatever replica I read it from, it's not out of date, out of sync from the master by more than 0.2 of a second. Or you can do version-based access. Or you can say, no, I got to make sure I absolutely have the most recent data. which means you direct your read operation back at the master node, and you're guaranteed to get a fully ACID type of transaction, from both a write and a read consistency perspective. So now we'll take a look at deploying a cluster, which you might think is difficult, but you'd be surprised at how easy it is. So to deploy a cluster, what you need to do is make a boot configuration for each of the server machines that you're going to run your database processes on. So what you do is for each of those, we often refer to these as storage nodes, you will set up the root directory where you find the binaries and where you store the data files on that server, along with the typical host IP address and the ports that you're going to communicate with clients on, and the ports that the nodes in the database server are going to talk to each other on in order to replicate and all of that. But one of the things you need to do is you need to set this capacity parameter. And what that represents is the number of potential processes that will run on that particular server. And those processes could be replicas or masters. And so they will be doing I/O. And so ideally what you really want to do is set that value to the number of disks that are on your machine in order to get the optimal configuration. But you specify the number of CPUs, the amount of memory, and we'll use all that overall system capacity to intelligently place the processes when we deploy this cluster and make it available to applications. So anyway, after you set up those boot configurations, you start them, and it's just a normal Java process. So you issue the start command to the kv store.jar and specify the root directory where you find those binaries and where you have your data files. Okay, so after you've set up your boot configurations and you started the storage nodes, the listeners, the agents, then you need to start an administration utility. And you can see here it's just a regular Java process. So it's the run admin command to this kv store.jar. And you do this for any one of those servers that you've started the agents on. And this admin utility is where you will plan a deployment topology. So this is where you'll specify how many replicas you want and those kinds of things. And this utility will let you verify that you've got adequate resources and that you can reliably place all the processes, and then it lets you deploy that validated plan. But all of the steps that you would do to actually set up that topology, you can actually put it inside a script, and then this utility can load that script to make it convenient. So what you will do within that utility is you configure the name of your store. You can see there on the top line. Here I've called it OnDB for the Oracle NoSQL Database. And then what you do is you set up your data centers, so which are an area of isolation within the topology. We talked about those. You want to lay processes out on isolated hardware units. So a data center is a unit of isolation from a hardware perspective. So presumably there's a server on there, and you, in this case, set up the number of copies that you want in that particular data center. And then you see the next line, you set up a storage node for each of the replicas that you expect to have inside that data center. So if I had said I had a replication factor of 3, well then I would actually have 3 of these specifications you hear where I say plan, deploy, storage node. There'd be 3 of those, one for each of the replicas. But the gotcha is it tricks people in getting started on this, is that after you set up one of those storage nodes, you actually have to deploy this admin service, which is going to coordinate all of those storage nodes together into a complete system. So you start that thing up, and then you go through and you add the other storage nodes to complete your topology. And then finally, you would want to give it a name and sort of create it, because you might create multiples of these for different database stores. So you name it, and then finally you validate it and deploy it. And again, all this is done within this utility, but you don't have to do it line by line by line manually. You can actually put all this stuff in a script file and then just ask this utility to load the script file, and it'll automatically deploy this stuff out. Okay, so now let's look at how the resource allocation actually works. So you create some sort of a topology that you're going to deploy, and when you say deploy it, we instantiate a number of processes that give you the maximum reliability for that topology. Okay, so what really happens? Here we have 3 isolation units. You see data center 1 on the top, 2 in the middle, and 3 on the bottom. Okay, and for each of those data centers, you have a replication factor that was configured. Okay, if you remember in the administration utility, we said, okay, for data center 1, we have a rep factor of 1, but in this picture we have 3. So recall that that you have to have a minimum number of storage nodes equal to the replication factor for your data center. So here, because I have a replication factor of 3, I put 3 storage nodes into that data center. Okay, and remember, each storage node has a boot config. Okay, and each boot config has a capacity. So to get the capacity of the data center, you have to sum the capacity of each of the storage nodes that is contained in that data center. So in this case, data center 1 has 3 storage nodes, each with a capacity of 3, which gives a total of 9. Okay, data center 2 has only a single storage node, which is equal to 8 in capacity, and so it's also the capacity of the data center. And then data center 3 is a capacity of 7. Okay, these are just arbitrary numbers, but this is how it works. So to figure out what your limiting factor is, your process limit, you take the capacity and you divide it by the replication factor. So in data center 1, we have a replication factor of 3, and so it's 9 divided by 3 is 3 in terms of your process limit. So if you go to the second data center, it's capacity of 8 divided by rep factor of 1, which is 8. And then in data center 3, it's 7 divided by 1, 7. So you see that 3 is the smallest number. So that actually ends up being your limiting resource when you go to actually instantiate the database processes. And so what will actually happen when you say deploy this plan that you're looking at is it will place one copy in the storage node in data center 3, and then for that copy it has to place another copy in the data center 2, only one copy because its rep factor is 1, and then when it goes up to data center 1, it has to have 3 copies, so it's going to deploy 3 processes. Okay, and so it repeats that. So by the time you get to the second and the third process in storage node number 5, you've had to instantiate 9 replicas into data center number 1, right? Through storage nodes 1, 2, and 3. And so at that point, you've hit the capacity of the data center. You can't deploy any more processes because you're at your max capacity. So therefore, you can't deploy yet another process into data centers 2 or 3. So that's why 3 became your limit. Okay, so just to give you a better understanding of how this works, imagine that you have exactly the same physical configuration, the same number of servers, the same number of storage nodes, the capacity of 3, 3, 3, capacity of 8. And in data center 1, instead you use a capacity of 1. Okay? And when you use a capacity of 1, that changes your process limit calculation, right? So now you have a capacity of 9 with only 1 copy, gives you a process limit of 9 in data center 1. It's still 8 in data center 2, and it's still 7 in data center 3. So the smallest number ends up being data center 3. It's 7. So 7 is the maximum number of processes you can have on any node. So if you look at the picture on the right, you can see, follow the same process. in your mind. If you put a process into storage node number 5, then you've got to have a replica of it in storage number 4, and then you've got to have another replica of it in storage number 1, 2, and 3, and so you continue to lay processes down in data center 3, and then you add the replicas to data center 2 and data center 1, and eventually, because you only need one copy in each data center, you lay down 7 copies in data center 3, in which case you reach its maximum capacity. So now you can't add any more, and so because you can't add any more there, you're not adding any more processes into data center 2 or into data center 1. So 7 became your limiting factor. And so you can see how profoundly this will impact the number of processes that are servicing requests as a function of the overall capacity of your data center and the replication factor. So there's a cool administration tool that will show you all this stuff as it's getting instantiated, and this is just a screenshot of it. But this stuff is really surprisingly easy to deploy. In fact, it's so easy, I'm going to just take a couple of minutes and do it live for you and show you, what it takes to deploy a reasonably complex cluster, right here on this laptop for you. All right, so hopefully we don't have any issues through this demo process, but anyway, so we open up a command interface, and I've got a couple of configuration files that are set up to sort of automate this whole process, so we'll take a look at them. So there's one called boot and start, and if you look at this, remember this is setting up the boot configurations, okay? That's the first thing you have to do, set up the boot configuration. You say where your files are kept, where your data files are going to be kept, what's the ports and what's the hosts, and here's our capacity. So here I've set a capacity of 3, etc. And so here I'm doing a whole bunch of these storage node configurations on a single machine. Normally you do this, for each server. So I'm playing with my ports a little bit here, but I think you get the idea. So I set up these boot configurations for storage nodes. And then I start all the agents. Remember, it's the next thing you have to do is basically start the agents for each of these servers. And then what you would do is, remember, we'd open up that utility. So here I have another configuration file where all I do basically is start this administration service that we talked about. And that puts me into the CLI that lets me create the topology, right? And if we look at the topology, it's a source file, because remember the admin utility can load a script, and so here's the script. It's I'm configuring a database named onDB. I'm setting up a data center 1, giving it a replication factor of 1, and so therefore I need a storage node for that data center, so I deploy a storage node, and then remember, after you deploy one storage node, you have to deploy this administration agent, so that's keeping everybody in sync. And so after I've deployed that administration agent, I deploy more storage nodes. In this case, also into data center 1. Eventually, I create data center 2 and set up some storage nodes for data center 2 and 3. Okay, and then I do something here we hadn't talked about. I create a pool to hold my resources, my storage nodes, which there's a default one. This is not really necessary, but I add all my storage nodes that I've created into this pool, and then I create a topology for all the resources in that pool. Okay, and then I deploy that topology, master topology. So it's really fairly straightforward. So let's actually do it and see what happens. So first we run boot and start, and that sets up all the boot configs, starts all the storage node agents, right? Now I start the admin utility. So first admin, and you can see that puts me into a CLI type of environment. And then remember, I can load a script. So now that I'm there, I say load this file, config store.source, which I just showed you, and that basically starts deploying the plan. So I can look at all this stuff inside my administration utility. If I go over here and open a browser and I point it at my local host 5001, where we started that admin agent, you can see that this stuff is getting deployed. You see it's dynamic. So you can see here in the corner it's showing I've deployed 9. Now I'm deploying basically more nodes. But it happens so quick, it's actually done. So it deployed the full topology here. And we can click on these and you can see the state of each of these individual nodes. But basically I just deployed a 9 replication node database server across 5 isolation units. And you can see, just because of the way things got laid out, I actually don't even have any processes running in storage nodes 2 and 3, but I've got them in storage nodes 1, 4, and 5. Okay, and so anyway, it just gives you an idea about how easy it is to do this. I mean, in less than 3 or 4 minutes, we just deployed a cluster of 9 servers. And so let's go back to the presentation. Okay, so one of the other things that's really neat is you can actually, when you deploy a plan, you can change it, and the underlying data will actually move and rebalance itself. So as we talked about splitting partitions, as you add more hardware resources, it's as simple as going back and executing another script in that utility. And in that process, you expand capacity and you add partitions, and so data spreads around in order to, again, to maximize the write throughput and minimize the read latency in the overall system, while providing that reliability in the underlying data and processes. Okay, so now we're going to look at actually developing an application. I mean, we've deployed a cluster, so we have a database that's there, and so now we can actually create an application to access it. So one of the things we need to talk about is that this is a distributed database. So one of the things we need to think about is how is it that we distribute the data around the store. And so we do that using a hashing mechanism on a key, and then beneath the key is a value. Now, a couple things to point out here. Number one, our keys come in 2 components, what we call the major key and the minor key. Now, the major key is the portion which actually results in hashing to a particular server process. So that's the thing that spreads the data around. And then the minor key serves to further qualify the data, but it does it in such a way that it localizes the storage in the same node as the major key component. So therefore, it optimizes the I/O when it comes to accessing multiple fields under a given major key, so in the hierarchy of data. The other thing to note is that the actual value that you can store underneath the key has options, right? And a lot of the NoSQL databases that are out there, they only store one type. If it's JSON, it's JSON. If it's a graph database, they store triples. That's it. What we do is we actually abstract that out, and so we can store multiple types for the value. We store binary types, JSON, RDF triples, and in fact we're coming with table row type of storage as well. So it gives you a lot of flexibility in your design. So anyway, this is the key structure, but let's look at how is it you think about this key and value structure when you are developing an application. And ultimately what you want to do is you want to think about this in terms of how is it that you're going to access the data in the application. So what are the queries going to look like? And what you want to do is you want to create these keys so that they're both lightweight, so that they're small and they fit in memory. So oftentimes you'll shorten what could be a long keyword. You'll shorten it into something which fits more appropriately in memory, or you'll do some sort of encoding. You'll encode into a hex format or something like that in order to shrink the size of your keys. But you basically set up your keys so that there is as friendly in memory as possible, and so that they model the type of query and access that you're going to provide and need in your application. And so in this case, for example, I'm setting up a key for what would be a pressure sensor, and I'm saying that the unique identifier for that key is the fact that it's from the left front and it has a particular sensor ID. So those two things together are a unique ID. And then notice the dash. The dash is what separates our major key from our minor key. So everything on the left of that dash is the major key, and everything on the right is the minor key. So in this case, I could have a minor key, which is a PSI measurement, or I could have an I rate, an instantaneous rate of change. So this pressure sensor could be measuring different things, and I could be storing values for those different measurements underneath that one major key, which is the pressure sensor. So what can I do with this? Well, again, it's all about your queries. So for example, I could, based upon the PS, I could do a query. It would be like a full table scan where I'm looking at every single pressure sensor in the entire database by just using a PS on one of my access methods. Or I could look at readings by section. So here LF is left front. So if I were to do a search on PSLF, then I would get all of the pressure sensors which are in the left front. So imagine I'm doing crash tests on a car, and I've got sensors all over the car, and I'm basically trying to analyze the impact that's going on in the crash test. So I could get, in one query, I could get all of the sensors that were in the left front quadrant of the car, for example. Or I could get a specific sensor. So the left front sensor with ID 123-PS3234, and just get that and get all of the data associated with that. So get all the instantaneous rate of change, get all the PSI measurements over time for a particular sensor. Or I could drill down even further and get into the minor keys, and I can say, well, for a particular sensor, give me just all the PSI measurements, or give me all of the instantaneous rate of change measurements for that particular sensor. Even further, I could go down, since I've got a timestamp on this thing, I can say, no, give me a slice of the data. For this particular pressure sensor, I want the instantaneous rate of change for the time period, between 3 and 4 seconds after the impact started, right? So you can see that you set the key structure up for a different set of queries that you might want to get at in the application space. And in this case, I'm talking about a sort of a crash simulation and pressure sensors that are wired into a vehicle for someone like BMW or Audi or Ford or whoever. Okay, but I think you get the idea. Okay, so we've designed our key structures for our application, and now we've got to get connected to the database in order to interact with the database and put data in it. So pretty straightforward. You've got a factory class, and you get a handle to the database by passing in some sort of a configuration, and then you use the handle of that database in order to do things like put and get, and we'll talk about that in more detail. So the thing to note is that when you set up the configuration for the handle to the store, one of the things you want to do is specify more than one of those storage node hosts. So here I've specified 2 of them, and the reason is just for availability and redundancy. Assuming a server went down, you wouldn't want to be blocked from getting new connections, and you can connect to any one of those nodes in the entire database. So you make sure to specify more than one. The rest of the things that you're concerned with in the configuration concern themselves with your transactionality. Remember we talked about you have a lot of control on how is it that you write through to the cache or all the way out to the disk, and how is it that you read things from any node, or for reading the most consistent data that exists in there. So you can set the store-wide defaults And then if you want to override those defaults, you do it on an operation by operation basis. Okay. So here's some basic code. This is a put example just to show you the kind of thing that you have to do. So here you can see that we're passing in a sector and an ID associated with the sensor, right? So we are constructing a key, which is that first PS part, plus a sector. So maybe it's the the right rear, or it's the left front, or whatever, whatever sector it is, plus an ID. So we're getting a particular sensor here, and we're taking in a reading, and we're converting that reading into a byte array because that's the value. Remember, in this case, we're just storing a byte array. So you've got a key and you've got a value. And what you have to do is wrap those things into our representation of a key and a value, which gives you a little bit of utility to work with those things, as some convenience methods. But aside from that, you take your handle to the database that we had before, your store, and you issue the put command, and you pass in the key and the value, and it's that straightforward. If you want to get it out, you see that on the next line, you have the reference to the database, the store, and you issue the API to get the key that's based upon that same sensor value, right? So we could have just used K here, right? But anyway, and what's returned from that is a value version, and we'll talk more about that later. But it's a very simple. I mean, this is all it takes to put data into the database and to get data out. So here's an overview of the read operations that are available to you with the Oracle NoSQL Database. Pretty straightforward. I mean, you can get the value beneath a key. You can get multiple values at the same time, but make sure they fit in memory. And it has to be to one complete major key. If you don't think it's going to fit in memory, then you can use the multi-get iterator, which returns it in chunks, or you could use the store iterator. And the difference being that the multi-get iterator requires the entire major key, whereas the store iterator, you can use partial key components. So basically, you can get the slices like a slice of the timestamp that we had talked about earlier, and then ultimately you can you use those with key range specifiers in order to filter things out and get just exactly what you want. And so the culmination of all 5 of these operators gets you all those different query semantics that we talked about when breaking down the key structure. Now, when you're doing read operations, you can get some exceptions that you need to handle in the application space. A consistency exception, which is, remember, you can just read from any node, or you can read a majority of nodes, or all the way back to the master. And so, for example, if you said you wanted to read from majority, but for whatever reason there was a network problem and you couldn't get to the majority, well, then an exception would be thrown. So you may have to handle that. You may want to retry, after you wait a little while or whatever. But basic kind of exceptions that you might expect in a highly distributed application. So you handle those, and you either abandon your operation or you retry, just like you would in a normal database application. So if we go on to writing, these are the write operations that are available to you. Very, very similar. You can put the value beneath a given single key, but you've got some variance on that. You can say, I only want to put it if it's absent, if one doesn't already exist, and if it does, you need to basically check the return result, and if it's null, that means it already existed in there. Or you can use put if present, which is the opposite of that. So it only allow you to basically, you're doing an update, and only if it already existed, that key already existed, do I want to update that. If it didn't already exist, return null, and then the application needs to check for that. There's also some versioning operations where you can actually grab a version when you first read a value out of the database, and then later on when you go to do an operation and insert it, you can say, hey, only do that if the version hasn't changed, right? So it's kind of like an optimistic locking similar to an optimistic locking model in a relational database. And then forms of delete. Just like with reads, with writes, you've got a few exceptions that can be thrown. In this case, it's the durability exception. Remember, so you're trying to write things all the way through cache to disk, or you're trying to get acknowledgments from replicas. And if you can't get all those acknowledgments, for example, you may throw an exception. So you can handle that exception. You can decide to, completely retry your operation, or just wait for a little bit of time and try to do the put again, or whatever seems appropriate for your given use case. And so this is an update example, and really this is just an update is the same thing as a put, and so this code just goes into a little bit more detail. In particular, we're showing you how to customize the durability. So we're doing a if you look at the try catch block there, there's a handle to the database, a store, and we're using this put if version operation. So we're using the equivalent of optimistic locking here. We've gotten a previous version from another time that we accessed the object. We made the update, and so when we're actually performing the update, we're making sure that we're matching the version of the value that we pulled out of the database before, to make sure some other process didn't update it. In the process, we're using a custom durability. So here we're saying that for my master, I want to set a sync policy of sync, so I must write to the master. But on my replicas, I'm saying I don't need to sync those. So I'm going to just, as long as I've written it out to the master, I'm going to assume that the system will handle the replicas, and I want to return. And then on the acknowledgement policy, I'm saying, give me a simple majority. As long as I've got at least the majority of replicas saying that they've received this write into their memory space. Again, I'm not syncing it, but at least it's into their memory space. They're acknowledging they have it, then I'm happy. Okay, and this is actually a pretty common durability configuration. So this is just showing how to customize this. Obviously, the exception handling, we could probably spend another webcast on that topic, but we'll have to save that from another time. We're starting to run out of time here. And some other stuff that I didn't talk about, Avro, for example, we can store Avro as the value type, and that allows you to have a little bit more control over the schema format and manage evolutions of the schema, etc. It's a highly efficient storage format, which is very popular, especially in the Hadoop space. Sequences, you can combine operations together, so that instead of doing 1,000 transactions for every timestamp, you could do one transaction to write all 10,000 values into the store. And then we've got some also specialized APIs to help you deal with things like images and all that, so we can parallelize everything and be very, very efficient about how is it that we both write it through into the store as well as help you read it back. So some more bells and whistles that are there, and obviously this is not a training lesson, so I encourage you to go and download the product, and then you can check all this stuff out. So use cases. Well, we're running out of time. I'm really not going to go into detail on the use cases, but this technology is highly suited for web scale type of transaction processing or personalization and real-time event processing. Those are the three major areas where we see people adopting the technology. There's a couple of examples there. Again, it's about dealing with data at scale and needing very, very stringent, low latency access to that data, or high throughput write operations. That's where this technology is best suited. And so here are some resources. You can go and get our white papers and documentation, download the product. There is a community edition. It is open source, and you can get subscription support for that offering. So it's very affordable. As a startup, you can get going on it and not have to worry about paying anything until you want. When you deploy, you can come back and get support. Or if you're an enterprise class customer, then we also have commercial licensing for you. And here, again, here's just some more resources. If you need to get a hold of anyone within the product management group, we'd be more than happy to talk to you. So give us a shout. And with that, I will turn it back over.